like to thank the organizers of this conference and for giving me this opportunity to talk about quantum theory, and this title is operational meanings of orders of observables defined through quantum set theories with different conditions. Quantum set theory is a set theory based on quantum logic. But maybe most of the audience don't like quantum logic. It's a traditional quantum logic you don't like, I think. However, set theory based on quantum logic is entirely a different field of the research. I will show. Because the quantum theory is quite useful, closely related to the standard quantum mechanics, but it has power to enhance or extend the standard interpretation of the quantum mechanics to very useful way. So we start with compare the quantum mechanics and classical physics. In classical physics, the physical system is represented by Borel space, and observable is Borel function. State is represented by probability measure. And then observable takes in interval I is represented by this formula for probability of this subset of the Borel space or phase space. In quantum physics, the physical system is represented by a Hilbert space. Observables are self-adjoint operators, states are density operators. And the same probability is represented by trace of the operator spectral projection for self-adjoint operator X corresponding to the interval I applied to or multiplied to rho and taking trace. So the entirely different formula, but they have the common interpretation. And our problem is as follows. In classical physics, not only in this kind of probability, just taking the value in some interval, but also in classical physics, they have the probability for equality and order as follows. So equality of the probability, probability of the values of x and y are equal is defined by this formula. And order, the value of x is less than the value of y, has this probability. So our problem here is that how should we define the probabilities for equality and order of the quantum observables? How do you define the probability for the event that x and y are equal, or how do you define the event of the x is less than y in the state rho? So this is not in the textbook or any standard interpretation of the quantum mechanics. However, this is very important. I have used this relation to justify our use of the noise operator induced quantum error. So in that case, we have shown that root mean square defined through the noise operator is equal to 0 if this happens. So this will show that this notion of the error is very sound definition. So now we consider the more advanced problem. How with the order of this observables? Our method to define the probability of the order in given state is based on the systematic use of quantum set theory. However, there are some problem using the quantum logic. because the quantum logic has ambiguity for conditionals, there is no unique definition for the conditional up to now. So we use such a, we have known that we have 3 candidates for conditional operation. So we study all of those candidates, then we conclude each conditional defines a quantum set theory in satisfying the GFC transfer principle. And this is very fundamental principle in quantum set theory, stating that the theorems of the GFC set theory has a good truth value, evaluated very nicely. And then equality does not depend on the choice of the conditional. However, order depends on the choice of the conditional. However, each choice of the conditional defines an order which have very precise and very clear operational meaning. So we will discuss what is the operational meaning of the order of the observables defined through the quantum set theory. Depend on 3 different conditionals. So we review quantum logic. So we consider quantum logic to be the set of the projection operators. So order is defined, negation is defined in this way. Then this is a complete automodular lattice. And the lattice operation can be rewritten in this way. Then quantum conditional is required the logical connective satisfying the following condition. If P and Q are commuting, then P imply Q has the same form as the classical logic. And then P and Q is equal to 1 if and only if P is less than or equal to Q. And this modus ponens satisfied and the modus tollens also satisfied. Then logical connectives satisfying those 4 conditions are only those 3 polynomials. So there are exactly 3 polynomial material conditions satisfying those conditions. First one is we call Sasaki arrow, and the second one is called contrapositive Sasaki arrow. The third one is called relevance conditional. Note that the classical form of this conditional does not satisfy this requirement. And we can characterize those conditionals using the range of the product of the projection. So Sasaki arrow can be characterized by range of the product of the negation of P or orthogonal complement of P times Q. And the contrapositive Sasaki arrow is the range of the Q times P part. And relevance conditional is just the infimum of those 2 conditionals. Then we can define the biconditional in this way for each conditionals. Then biconditionals are common, it's the same. So using those 3 conditionals, the biconditional reaches the same logical connectives. So if you consider the biconditional, you don't need to check 3 different cases. However, we have to check each conditionals if you consider the order of the observables. So quantum set theory is defined as follows. Given the ordinal alpha, we define V alpha Q. This is alpha quantum set universe based on quantum logic Q. This is a kind of the fuzzy set. Domain we write du because this is economy of the number of letters. DOM takes 3 letters. It's serious if you write a long formula. And so V alpha Q is a function, set of the function from its domain to Q, and that domain is a subset of the B beta already constructed. Then Q valued universe is defined by the totality of the union of the all B alpha. Alpha moves all the ordinal numbers. Then
Q is some orthonormal base, for example?
No, it's Q is a set of the projections, all the projections.
All the projections in the Hilbert space?
Yes. Or equivalently the lattice of the closed subspace of the Hilbert space. Closed subspace.
Process?
Subspace.
Because I have seen something similar in Boolean valued set theory.
Yes, yes. Boolean value set theory starts with Boolean algebra B here. And the construction is almost parallel. But we use not Boolean algebra, but projection lattice of Hilbert space.
So the whole orthomodular lattice?
Yes, yes.
Okay.
Okay. So it's very convenient if you know Boolean value models. Construction is quite parallel. Just the difference is using not Boolean algebra. Then we can define the truth value of all the formula written by language of set theory. So equality is defined in this way, and epsilon relation is defined also in this way, and we use those two formula in a recursive way based on the rank of the quantum set. And then composite formula defined for usual way. Then according to the and then we also embed original universe of ZFC set theory into this VB in some standard way. Then we can show that if formula is true in the original universe, then embedded formula is also true. And in order to explain the transfer principle, we need to introduce commutativity of the quantum set. For any subset of the quantum logic, the commutant of the subset is just defined through the very similar way to the commutant of the operators. Then a commutator of this subset is defined through this way. This is just the largest central projection on which this restriction is commutative. And then the support of the quantum set is defined by recursion on this the rank of U in this way. This is just the element of Q which is needed to construct quantum set U. Then a commutator of the sequence of the quantum set U1, U2, Un is defined by the commutator of the support of all of these quantum sets. Then we can formulate the transfer principle. For every formula if this formula is provable by the GFC axiom, then this truth value just defined through those rule is always satisfies this relation. So the truth value is, if the formula is a theorem of the GFC, the truth value is always larger than commutator of those quantum sets. And then we can show that what is quantum real number means what is a real number in this model. We will show that the real number in this model is just one-to-one correspondence with quantum observables. In order to construct, we start with the rational number. Then the rational number is just correspond to the embedding of the standard rational number. However, direct embedding of the real number cannot be the satisfied property of the real numbers in this model. In order to define real number, we use Dedekind cut definition. Then the predicate meaning x is a real number is expressed by this set theoretical formula, and then we define the set of the real numbers in this model is just the element of the universe satisfies this formula, and some additional condition about the common domain. Then,
But Professor, I think if you want to use this kind code, you first have to define the natural number, right?
yes, natural number and rational number is just the embedding of the standard natural number and the standard rational numbers. However, the embedding is this one. This is just a 0-1 valued quantum set. It's very trivial.
Yeah, okay.
However, the direct embedding of the real number cannot be a real number in the model. So we use the Dedekind cut definition to define the real numbers in the model. Then we obtain the following theorem. There is a one-to-one correspondence between the real number in the model and the self-adjoint operator on this Hilbert space. And this correspondence, just the spectral projection is just the Boolean, not quantum set, quantum logical value of the set. Then equality of the quantum observable is considered using this embedding. So you are given the two observables A and B, then you have the embedding in the quantum set universe. A tilde and B tilde is just corresponding real number in the model. Then A is equal to B is this formula and this formula. Then we show that we define the probability of the observable A and B are equal in the state of psi to be the usual Born formula using this projection. Then this definition is independent of choice of the conditional because the biconditional is independent. Then we can have the characterization of the equality as follows, but today we skip and we consider the order of the self-adjoint operator. And this is a definition of the spectral order of the two self-adjoint operator x and y, defined by this condition. Then this spectral order coincides with the linear order for projection or commuting self-adjoint operator. Linear order is just the usual order. And then this spectral order is equivalent with the linear order for nth power of x and y. And then for any self-adjoint operator, this quantum set theoretical order has this truth value. It depends on each choice of the conditional. However, we have shown that this truth value is equal to 1, is equivalent to the spectral order for each choice of the conditionals. Now we consider the particular, for the particular state, what is the probability of those order defined through the quantum set theory. In order to that, we assume the Hilbert space is finite dimensional, and we define the joint probability of obtaining the outcome x is small x, y is small y. In the projective measurement of y immediately followed by measurement of x. This probability is given in this formula. Here, if you start with the state psi and measure y first and then measure x second, then the joint probability of the x and y is given by this formula. And also, if you measure x first and then measure y second, then the joint probability of y and x are given by this formula. And then we can characterize the order in this way. So order defined by Sasaki law is probability 1, if and only if this probability is equal to 1. This probability says that if you measure y first and x second, and then x is always smaller than y, or this is just the same as this probability. And if you consider the order defined by contrapositive Sasaki law, then this joint probability has a different order. And if you use the relevant conditionals, you have the both happens. So we have the following conclusion. In quantum mechanics, we can define probability of equality and order relation for observable. The equality is defined in this way. The order is defined in this way, using each choice of the conditionals. And equality implies the commutativity, and equality is characterized by this formula. Then order depends on the conditionals, and order defined by Sasaki law is this. This is just an inference from the past large to future small. So if you measure the y first, and if you obtain y, then you conclude the x measurement followed by y measurement always smaller than y, if state satisfies this condition. And contrapositive Sasaki law has the opposite time order. So this is inference from past small to future large. And if you use the relevant conditionals, this joint probability, or both of joint probability is satisfied equal to unity. Thank you very much.
Questions?
Professor, you will say then that the relevance will be like more conservative than the other?
Yeah, more strong.
Not stronger. But I don't understand what it's the meaning of past large and future small, or...
Yeah. In this, if your state satisfies this condition, then what is this meaning is that this means that in this state, this order relation is true. And that means what is this order relation in operational language is as follows. If you measure y first and x second, then measurement result of y is always larger than measurement result of x. And if you define the contrapositive Sasaki law, this relation holds if and only if you make a joint successive measurement, x measure first and y measure second, then first measurement result x always smaller than y. So those two operational condition is different, and such a difference is occurred from the choice of the conditionals, which define the order.
I have a question about concept theory part. So you have this correspondence between embedded real numbers and self-adjoint operators. But are those self-adjoint operators also bounded?
No, not necessarily bound.
Do you get, since in an orthomodular lattice, not you can't always find an order relation between two elements, like one will be neither larger than the other, nor smaller, nor equal. How does it reflect when you compute the probabilities? Does it like produce inequalities or something?
Oh, in this case, in a given x and y, not necessarily the one of which is satisfied. However, there is in quantum logic there's excluded middle satisfied. So this satisfied or this not satisfied.
Okay, so do they like complementary
Yes.
probability sum up to 1?
Yes.
Oh, that's
In
great.
this case, there are opposite inequality satisfied. So if this is probability 1, then negation of this relation is probability 0.
But the negation doesn't necessarily is not simply related to the other condition.
No, not necessarily.
Yeah.
Okay, thank you very much.